Well, is she still there?
Yeah.
Oh, okay.
I think if you spotlight both the virtual, yeah.
Vanessa, can you hear us? Can you share your screen as well?
Oh, now
There you go.
Okay. Okay. Okay, so I guess I will take questions for all three of our panelists.
Maybe I ask one. Yes, I got the microphone. So the first question is for Georgia. So you see that you have this structure for your confounding factors, and then you'll be able to get some reasonable like identifiability conditions. That reminds me of the independent component analysis when you have a time series structure and you can do the Gaussian work with the dependencies. But in independent component analysis, they also have this non-Gaussianality assumption, also give you some identifiability there. So I wonder what you think the non-Gaussianality might also help you in the spatial case to get reasonable identifiability.
So can you hear me? I don't know. This is something that I've been thinking a little bit more recently, because I saw this presentation by Jonas Peters that he talks about how having extreme observations can help you learn causal relationships more. And I think that that's related to the lack of Gaussianity, essentially. So I don't think it's necessary. I think that perhaps by having lack of Gaussianity, we can look at these tails and learn something that we cannot learn with Gaussianity. I think so. I don't know. I've read that paper, but I don't know much of that other literature on that about the time series problem you bring up. I think those two problems are very related. Essentially, the way I understand spatial confounding now is that essentially you want to get rid of everything that is structured so that you can essentially use the independent residuals of an exposure model and regress the independent residuals of your outcome model and those residuals of the exposure model. So I think that this is essentially the connection for time, spatial, and I think also network data, that as long as we get rid of everything that has a structure, what remains has to be the exposure effect. And there was something else I wanted to say. So I think that's the connection that comes to mind. I don't know if that answers your question.
Thank you.
Thank you. So I have a question for Luke. So, you showed us that it's very important to pick, your S demand, and even the different, finite population versus super population, how all these different variants, estimators behave in very different ways, depending on the assumptions that you've made. And there's a lot of nuance here, and it's nice to see it all in one place. I guess I'm wondering, I've not talked to people that run large scale experiments too much, but I'm wondering if people might say, oh, I don't want to have this kind of nuance. I guess I just want a one size fits all approach. To me, that seems like it can't really happen, based on all of the nuance that you've shown us here. Have you had conversations like that? And if you have had conversations like that, how do they tend to work out?
So I've had a few, and my collaborator has had more, because he works on the ground. He works at MDRC, where they basically do these sorts of evaluations all the time. And he's one of the people that people come to bother when they're trying to figure out what to do, or they just need an answer for something so they can go about their business. I would say I actually secretly in my heart feel that there is a one size fits all answer for most cases, which is to just fit the finite sample person weighted estimate. I don't believe in the ability to generalize out of an experiment in any kind of reasonable context. These samples are always convenient samples. They're not necessarily representative of the target population. It's rare that there is a target population that anyone can really write down, which means, and also in the social sciences, we struggle so much figuring out if things can work at all that asking the question, did it work for the people that I tried to impact, feels like a big enough question to keep anyone busy. This is not an answer that people really like that much. Telling them that generalizing is just not a thing is really, that's a difficult conversation. And because of that, there's this large literature about generalization where you try to reweight your sample to match the characteristics of the population and so on and so forth. And you make a series of heroic assumptions along the lines of most quasi-experimental assumptions to say that it's going to be fine. And you get bigger standard errors, which probably are going to hedge your bets in a nice way. But at the end of the day, I think, and that's the conversation I think to have with at the intersection of this work, which is to use an estimator that's assuming your sample is a superpopulation, a sample from a superpopulation, I think is a very lazy way to go about generalizing. And we should possibly be dissuading people from that and instead saying, okay, if you want to generalize, let's do that as a second step and talk about what it means to generalize. That being said, there's a lot of strong arguments I've had with other people saying, well, actually, people aren't going to do that. So having a standard error that at least generalizes to something is better than a standard error that people are going to very quickly forget means that you're only talking about the sample that you have. And I think that's also a strong argument. So I find myself confused at that point, and then I sort of go off and to a corner and sulk. But so that's my current thinking on the problem. And I'm all excited to talk about it ad nauseum as to what the right thing to do is. I think your question is really right on in terms of where we need to take the field in terms of applied practice. Thanks for the question.
My question is for Vanessa. And I'm coming from a potential outcome framework perspective, and there might be some aspect of the DAG formulation that I'm kind of missing in some assumption or some idea. But and I like the emulating trial perspective, but you're talking about hypothetical interventions. So we are imagining some intervention that might not exist today, but could exist at some point in the future. And from my perspective, it seems that if it is a hypothetical or an abstract intervention, there's a big space of possible social interventions, and the big space of possible interventions could have different effects. So but it seems like you are defining a specific effect. So how can we think about that specific effect in that space of possible hypothetical interventions? I don't know if my question makes sense. But...
Well, I think as the more specific you can be, the better, because then you know more specifically what you're actually talking about. If it's very, very hypothetical, so you know there's a scale of very specific to very, very, very hypothetical, and the more specific you can be, the better you can talk about the assumptions and whether they are plausible or not. And the more hypothetical things become, the more difficult it might be to justify the assumptions. Or you know, you're talking about something that's very vague and very in the hypothetical future. So and it's a matter of the subject matter, and I've tried to give real examples, not just where it remains entirely hypothetical, but where people have thought about what the different components are. And when you sometimes, as I said in my talk, sometimes it's useful to think like this. And sometimes when you talk to people who do mediation analysis and you ask them, why do you want to know this? Then they do come up with a story that's exactly a separable effects. They talk about different treatment components, because most treatments that we look at in practice really are do consist of several things. You know, every treatment itself has, if it's a medical treatment, has the active ingredient and the placebo effect, for example. That's already two components. You know about being treated, and there's actually some chemistry going on. So that's already two different components. So when you ask really why are people interested in things, then some of the time, I wouldn't claim most of the time, but they come up with a separable effect story.
So this question is for Luke. So I really enjoyed the talk and really just the distinction between all the design-based ways and the different ways of estimating effects across sites. One thing that I wanted to ask is something at the very end of your talk about covariate adjustment. So I noticed sometimes, first, I guess one specific question and one general question. One specific question is related to, in your work and maybe in others' work that you've seen, do people adjust for the cluster size as part of the covariate adjustment? And the more general question is, when you think about covariate adjustment in multi-site trials, I noticed that at least when I talk to some applied folks, they try to distinguish between cluster level covariates and individual level covariates. And I know those two things could have different impacts on inference. And I just wanted standard errors. I just wanted to hear your thoughts on those two questions. Thank you.
That's a great question. And I was a bit glib with the covariate adjustment. So with covariate adjustment, we focus on adjusting for individual level covariates. When you have a site or cluster level covariate for a multi-site trial, if you actually think about, since you randomize within the site, whatever impact that covariate is going to have is going to automatically get canceled out if you look at sort of the treatment and control difference within the site. The way you can actually include a site level covariate to improve precision in a multi-site trial would be, in principle, to include it as an interaction with your treatment effect to try to model the treatment variation across the sites. But as far as I can tell, that doesn't seem to increase precision unless you have very, very strong relationships for estimating that overall average impact. So there's a side project which it has stalled on my part of trying to think about what do you do with covariates in a multi-site trial when you randomized at the individual level? Are those site level covariates useful, including cluster size? Like how can you exploit them to do something? If you're interested in treatment variation, I think you can look for relationships with respect to those covariates. But if you're just interested in some average treatment effect, I'm not sure what they have to offer, but that's an area that I'm just ignorant. I'm still thinking about what that means.
This is a question for Georgia. I really like this sort of connection between spatial statistics and causality, and I know very little about spatial statistics. So in some sense, this question is naive or perhaps more philosophical. And so can you say a little bit more about how I'm supposed to understand a spatial effect? So what I'm wondering about is that to what extent is the space actually causal, or to what extent is the space a proxy for other causal effects that are at play? And it's really a conceptual question, if you could comment on that a little bit, of how I should think about that as separate or the same as a causal effect.
Okay, so there's kind of like two parts to that question. The second one, I'll start from that, is how does space play a role? Is it an effect of space, or is it an effect of the treatment itself? It's connected to the previous question. If you essentially get rid of all the spatial information from your data, then it's the treatment that is left that could have the exposure effect, that could have an effect. But how you define it, I think actually, so if you have a binary treatment, I think it's one thing. If you have a continuous treatment, I think the estimand definition plays a big role, because I don't think that it's necessarily reasonable to think of YZ with Z being the same for every location. So if your Z is a continuous exposure that is spatial, I think if you wanted to talk about the causal effect of that continuous exposure, you would have to consider alternative little z's that remain spatial and perhaps resemble this delta interventions, like Ed Kennedy has this paper that like perhaps like shift the structure up and down slightly. That's how, but I think that that's related to how you define causal effect in the spatial setting. And the second part of like how actually you deal with space. The way I understand it as the safest way to separate exposure and space is by ensuring that your exposure has in reality some independent component in it. That if the exposure itself is perfectly spatially smooth, then you cannot really separate them without assumptions on the range of spatial confounding. Like you can assume that your spatial confounder only varies at, like has like a decay with a range parameter that is something, then you can regress that part out. But if your exposure is perfectly smooth and you don't want to make any assumptions, I'm not sure that there's much progress you can make.
Okay, I have a question for Luke, but also on this topic of spatial structure. So perhaps one heroic assumption that gets appealed to for generalizability or in a superpopulation framework is that of spatial structure across sites, maybe related to covariates and sites. And this kind of heroic assumption gets made maybe a little bit more in the machine learning and domain adaptation literature, imposing some kind of metric structure on the outcomes or the covariate distributions across multiple sites. Are there situations in which it is possible to use more of that structure where those assumptions may be more appropriate than in other settings, do you think? And this is perhaps related in spirit to a lot of multi-level modeling and hierarchical assumptions, but perhaps of a different flavor.
Wait, I think I missed it. So you're saying that in the context of a multi-site experiment where the sites themselves have a spatial orientation with respect to each other? Am I following you?
Yeah, whether there are situations in which that kind of spatial structure could be more closely leveraged, or whether that is more closely related to like interference modeling or exposure modeling.
I think you would end up, in that case, you'd end up with like interference modeling, which then introduces a lot of complexity that I've always been personally afraid of. So I don't have much to say about whatsoever. There is something very attractive about I do think that there's spinning your question a little bit. I do think that there's a lot of cases, especially in quasi-experimental, this shows up a lot in spatial IV designs and things like that, instrumental variable designs, where it feels to me like the spatial structure is ignored in a lot of what you see out there and what's being done in practice. Like people sort of get a bunch of their units that are arranged spatially, and then they neglect that spatial relationship in the analysis. And I would really like to see that come back. But some of what you're saying also sounds like where you would use the spatial structure and try to estimate treatment effect as a function of location, looking for sort of treatment variation along spatial lines, which I also think would be an exciting direction, but I don't offhand, I think there is work on it, but I'm just not as intimately familiar with it. I feel like I haven't really answered your question, but that's what I got.
So here's a question or maybe clarification for Luke. So if I understand correctly, you are doing a very nice stability analysis for different estimates and different methods. Are there methods kind of for the same estimates and can be, because when you have data, especially when the design aspects very unclear, the practitioner probably end up using different methods to make a decision, right? And one question I was asking, if you, like in our PCS frameworks, I usually try to screen the different methods using some reality check, say prediction, and then look at stability analysis. Do you think that's a relevant angle for what you do here? Like if some of the methods don't really fit the data, then why do you care about how the estimates turned out? I know some of the design will eliminate some of the competitors, but I would assume that there could be competing estimators giving a data set.
So I think in this particular context, one of the nice things is that the design behind the data is usually very, very clean. Like you've identified the sites, and the randomization of treatment within the sites is understood to, like, people do a good job actually randomizing. So it really is a driver of your, it allows you to directly get your causal effects without worrying about confounding. That being said, I like the idea of the screen, and I think we sort of did a baby version of that by sort of identifying that some of these estimators, like of all the various ways of estimating data, we identified that some of these estimators are after a different thing than other sets of estimators. So by dividing the estimators into sets, I would say that the stability that we really care about is how much we see our point estimates and inference changing within all the estimators that are aligned to estimate the same estimand. And when the estimands are different, for example, if going from finite to super or vice versa, then you would see these radical changes, but we have an easy explanation for the radical change, which is that they're actually answering different questions. So of all of the things that we identified as reasonable ways of analyzing the data, I would say that we find a pretty good amount of stability in most of the contexts. The one exception being the superpopulation site. And perhaps there are other estimators that could be used there that would be more stable, or that there'd be a way to get a handle on the instability. And that's an interesting question, and an area that deserves further thought.
Yeah, I think the screening with the kind of type of problem, I think it's a very nice one, but I was asking more like, do you worry about before you go for this estimate to see in general, does the model fit the data?
Oh, like, do we do model checks?
Yeah.
We didn't. We just sort of applied the models because all of the models most of the models aren't really relying on very many parametric assumptions. So in principle, asymptotics is going to kick in unless you have pretty serious outliers because of the randomization. The randomization saves you from a lot. It would be interesting to go back, and some of the models do at least nominally make parametric assumptions. Again, in practice, it seems like randomization allows you to ignore violations of those, but that's something that I'm saying feels true rather than a strong statement. So it's probably worth looking at that more carefully.
Thank you.
Thank you.
This is a question for Vanessa. On your last slide, or towards the very end of your presentation, you had the comment that the account you give is restricted to a single world. So I was wondering whether you could comment a little bit more on that, and to what extent you think that sort of restriction is important, or should be paid attention to, or that what is its value to stick to a single world?
Well, so in the context of mediation, causal mediation analysis, you have these crossword quantities where you imagine the treatment is being set to one thing and the mediator is being set to what it would be had the treatment been something else, which is not only a long sentence, but it's also complicated to think about and involves assumptions about these crossword quantities. So what would happen with the same individual under one setting of treatment and the mediator under the other setting of treatment, etc. And so by thinking about it with the separate components of the treatment, like Jamie, Ilya, and Thomas described it in one of their recent papers, you can think of it as a four-arm trial. And that would be something like a target trial that we could do in this world, in a single world, where you can so you have these components of treatment, and you think of the two values for one component, the two values for the other, and altogether you have four combinations. So it's a four-arm trial. And if that is meaningful in the sense of
as we were discussing earlier, less on the specific side and less hypothetical side, you can think about this trial and maybe even carry it out in the future in a single word. And that helps, I find, it helps to think about the plausibility of various assumptions that you need to make, in this case, for the identifiability. Does that answer your question? It's very weird to not be able to see the people who are asking the questions and to see whether they are nodding.
I am. I'm nodding.
Okay, good.
You and Luke are larger than life, so we can see you very well.
I don't see any. Should we? Okay, so thank you to our panelists and thanks everybody. And that's it for now. And we'll be back here at 2 p.m., right?
Yes, we have lots of session at 2. Thank you.
Thanks so much for having us.
Thank you.